Let me just start with what we're not. And we're not offering a Cisco modeling lab or a container lab or a Virl environment. We're not so focused on the iOS version of the Cisco device, and if you upgrade it with the new features, how is that going to impact the network? We call it an operational twin to differentiate a little bit from the digital twin in that that massive amount of data that we have is the state of your network in the past and with predictability into the future, and obviously the present, right? So again, more needles, Internet of Things, globally distributed network, hybrid clouds. Downtime impacts revenue and SLAs, right? Downtime, I read some articles, something like $600 billion worldwide from network outages. 75 to 80% of those are human induced. And the complexity of these networks, the needles in the stack of needles. So what is the operational twin? It's a real-time digital representation of your network with live and historical data for deep visibility, and it enables safe experimentation without impacting the network through natural language interrogation. If I were to change the path on this, if I were to put this BGP in, if I was to remove this network, if I was to add this subnet, safe thought experiments using real data and real predictability. Now, how do we build this? How does this happen? It's not easy. This is a very complicated problem to solve, but we have, again, optical services, device layer 1 information, all the way up to layer 7, offering real-time state, configuration differentials at any point in time between any device, control plane and data plane visibility and the physical topology. I'm going to focus on the DVR capabilities in the video, but here is sort of the dashboard of the DVR. So this is what the path looked like, right now. That is what the path looked like yesterday. It looked like 2 days ago. A full Google-like experience overlaying your traffic with geolocation metadata. So let's watch the video, and I'm going to pause this one a few times because there's some things to highlight here to set the stage. So what are we looking at here? This is an internet path tab that we specify an ingress PE and then the internet address of 8881, so a Google address. So this is how that PE reached the internet from one side of the country to the other or across state lines, right? So what we're going to do is let the video catch up a little bit.
While we're waiting for that, John,
yes.
Quick question. How does it determine that? Is it based on like the routing table? Is it based on ICMP? How does it actually determine the path?
Yeah, it is based on the routing tables and the forwarding plane information.
Okay.
Yeah. So what we have here is a couple of widgets showing the path time, which is kind of a neat concept, right? The time of the path. Here's, 0305, 0404 at the exact same timestamp. So at the same time of day across different days, and when he clicks on the path, we're going to see that we can drill down. So we can click on the topology view. We can click on any of these links. We can drill down and see that that device has 3 edges. We can drill into the edge nodes and drill into the topology view. It's fully interactive view based on the metadata and the forwarding plane. So now he's going to change it to another date and time, and we can see that this part of the path is different. It got highlighted. So we have a different start and end for our path to the internet, which is using different devices, and we can interrogate those devices. The next thing we're going to do is change to infrastructure paths. And infrastructure paths is between an ingress and an egress router. Just 2 random ingress-egress routers. This is how the traffic got all the way across the country. Your providers, your links, your IP addresses, everything you'd want to know about it. And you can long press for details. You can see the number of edges. Here's the edge nodes. You can actually click and see what interface is facing what other interface. Really remarkable stuff. Great to compare against intent, because we'll give you the full path as a text string, and you can interrogate that against your intended path. So can we do this through the copilot? Right? I could use the classic web way and click and find and sort and filter and blah, blah, blah. Or I could just say, show me the path from this PE to this PE in natural language. There it is. And we have two answers. We have the, actually, this doesn't have the copilot enabled. But we have the path here just from the natural language prompt with a fully interactive dashboard. We can see we can click on show and see the different PEs involved and different devices involved. And one of these buttons is actually going to show the entire path. This one. So this here, you actually see from one end of the country to the other end of the country, every interface that's involved, every bundle that's involved, core routers, PE routers, the whole thing. And we could change this time scale like a DVR. Show me yesterday, show me right now, show me a month ago. Now the last one we're going to show is very similar, but it's going to be L3 VPN paths. And in this case, we can put the VPN and the customer and the route. So if you are running multi-customer environments or multi-MPLS or whatever, you just can adjust your customer corp to get the path through for L3 VPN.
I have done, and it's regarding, sizing on, if you've got hundreds or thousands of devices in your network, this could potentially be a huge amount of information to Selector to ingest and process. So what are the methods Selector uses to ingest the information, and what method you're using to kind of guarantee that you're not dropping that information, that you are actually getting a true DVR-like experience, and getting information around all the information around potential routing changes and things like that. That could take time. How do you mitigate that?
That's a great question. So in terms of scale, one of our largest customers, I believe the 24-hour data lake is 1 terabyte. Can you believe that? That's just logs and metrics. So we can handle very extreme large-scale networks simply by scaling our nodes, and we ingest everything into a Kafka bus. So we're monitoring the bus, we're monitoring the nodes. We have Kubernetes that will auto-scale the pods. So if there's let's say there's a fiber cut and suddenly there's a huge reconvergence and now suddenly I'm advertising routes differently, right? That's almost like a mini catastrophe when that happens, right? So our pods in Kubernetes, and it actually leads me to this next slide, so I'll put the slide up. The pods auto-scale. So when there was a hurricane that caused a massive increase for one of our customers, within 5 minutes, the Selector Kubernetes had auto-corrected and auto-scaled the pods to handle the massive influx of information. So Bruno, to answer your question, I think it's baked into our architecture as a microservices architecture that can scale horizontally as it needs to, or vertically as it needs to. And in terms of scale of our customer base, right, it could be hundreds, it could be tens of thousands of devices, and we simply just continue to scale the number of pods. So we have collector points on-prem that feed the cloud. So there are certain data collection points. But if we look at the bottom, this is the Selector stack in 4 layers. The collection service, the data hypervisor, the knowledge service, and the collaboration service. So we've really been heavily focused today on the top of this stack, the collaboration services through Slack or Teams, through a web GUI, through a REST API, through GenAI, soon through MCP, through a Jupyter notebook, excuse me. And these are all individual microservices. So if Slack has a huge demand, we just scale those pods for that particular microservice. Now, when we move into the knowledge service, this is really that network language model. You can see it in the center here. And it comes with its own query engine, alert engine, notifications, and it's fed, right? This line here is us fine-tuning this network language model with the telemetry from the bottom parts of the stack, right? There is a hypervisor. Now, the hypervisor is just like a VM hypervisor, except it's for data. So when data comes in one form, another form, JSON, XML, custom, text, we want to normalize all that and make it homogeneous through the data hypervisor layer, and we have different transformers that do that. Finally, we have that ingestion engine, Bruno, to your point, where we can take things in from REST, from Splunk, from Influx. We can feed from your own customer message bus if a customer is running their own Kafka. We can take it in from routers and switches through SNMP and syslog, obviously, and also through GNMI and streaming telemetry.
Quick question for you.
Yes, please.
Jason Ginner. Where do you guys host all of this? Is it like some of it in public cloud, some of it like on your own private infrastructure, or is it?
It's kind of a mix. So for a customer, there's going to be some collection engines on-prem to get the data out of their on-prem infrastructure into our cloud.
Sure.
And then the upper layers of that stack are hosted in either our cloud or the customer's cloud or the customer's on-prem. It's totally a flexible deployment model. But like I said, think of this as a per customer silo.
Okay.
Right. So there's no cross pollution between customers from ingestion layers or sharing data or anything.
Is your stuff hosted in a specific public cloud? Like, are you guys at Google, Amazon?
Yeah, I believe we are using Google.
Okay.
If you wanted to host it in Selector's cloud,
okay.
I believe that's in the Google cloud.
Okay.
Yeah.
Thank you.
The other thing is Varija Sriram, who is a founding engineer at Selector, a brilliant architect and engineer. Her and I are doing a podcast at the end of the month, blowing up this architecture and really doing a deep dive. So if there's any questions about, if you're curious about how Selector builds this or our architecture or our Kubernetes or how we scale, tune into that podcast at the end of the month.